So for my additional facts slide, I have that J.J. Thomson also discovered isotopes and helped develop mass spectrometry, which is still used in chemistry today. I also have that he worked with other major scientists, including Ernest Rutherford, who later discovered the nucleus. Thomson's students and co-workers won several Nobel Prizes, showing how influential his lab work was. So his work also proved that atoms have smaller parts, which helped start modern atomic theory. His son, J.P. Thomson, also won a Nobel Prize, showing physics ran in the family, which is pretty cool. So for my additional interest, I thought that it was interesting how tiny an electron was, the charge was, yet it controls so many things in everyday electricity. And I was also surprised to learn how many safety issues that they had back whenever all of this, in the early scientists they had. It just shows that technology really has helped us with our scientific discoveries and how we go about our labs. So if I were to investigate anything, I would want to investigate how an electron charge is used in medical imaging, because I'm going to be a sonographer. That's what I'm studying for. I want to specialize in OB sonography. So this really sparked my interest. So I also want to explore how scientists measure single electrons today using advanced technology. I think that is so neat that they can study something so small. And so for my overall summary, so how it went. Overall, I thought that this project worked out very smoothly, and I have learned more about the electron charge. So the most important thing was that I'm now understanding better how an electron charge is fundamental to electricity and circuits. So the easiest parts of the project were the gathering the formulas and the constants for electron charge and applying them to simple circulations. The hardest part was visualizing an electron flow in circuits and interpreting the results for more complex setups. The most surprising part, I was surprised at how small an electron charge is of one single electron, and how it's crazy that it powers a whole circuit, and when you combine it in large numbers, we get electricity in our houses. So then I have my relevant sources slide. I have a picture of the book that I used, and I listed them all here.
Hi, my name is Julie Acosta, and this is my part E of the electron charge in my lab class. So the additional facts that I learned during this, it takes about 6.24 times 10 to the 18 power of electrons to equal just 1 coulomb. That basically just shows us how small and tiny the electron charge actually is. Another additional fact is that a proton actually has the same charge as an electron. They're just different signs. So one is negative, and then the proton is positive, and then the electron is obviously negative. And another fact is that the electron charge can never measure half. So it always has to be a full number, and this was proven by Millikan in his oil drop experiment. Now, the additional interest that I did have during this project was I found interesting that the electron charge works the same everywhere. It will always be the same everywhere, no matter what the temperature is, the pressure is, or the location. It's always just going to be the same. And I didn't know that, so that was pretty interesting to know. Another thing I did found interesting is that without the electron charge, there would be no chemistry. So the electron charge literally controls all chemistry, and we wouldn't have it at all without the electron charge, which is also a pretty big thing that we have. It's just very interesting to know that something small can have that much power, and it obviously creates light, electronics, and all that. So I just find it super fascinating that something small can create stuff super huge and very useful. So the overall summary would be, overall, I did think the project went good overall. With my partners too, it worked out really good. I learned a lot than I actually thought I would. I didn't really think there was just more into it than just being a charge. Some of the most important things I did learn is that electron charge is actually the reason we have light, electronics, medical imaging, and it's just fascinating again because it's like, what if we didn't have the discovery of the electron charge? It just makes me think, would we even have the medical imaging, light, electronics, all of that? The hardest part of this project was finding the original experiment. They really didn't have a lot of information, and if they did, it didn't really seem accurate because everything just said something different, so it was pretty hard finding what the original experiment was, and it just took a lot of reading and a lot of websites to find. Now, the easiest part of the project was just me understanding what the electron charge actually does and how it works overall. And then again, the most surprising thing, just how I also put it as the most interesting thing, is that again, the electron charge is the same everywhere. It's also the same on Earth, in space, stars, galaxies. It just never changes, it's always the same. And these right here are just some of the relevant sources that I did use during this project and overall.
Additional facts. Robert Millikan's oil drop experiment in 1909 was the first precise measurement of electron charge. The electron charge is exactly equal in magnitude, but opposite in sign to the proton's charge, ensuring charge neutrality in atoms. The concept of quantization of charge, all charges are integer multiples of the electron charge, stems from all this discovery. Charge conservation. In any closed system, the total charge remains constant. Electron charge plays a role in electric currents, where current is the flow of electrons. It is essential in technologies like semiconductors, particle accelerators, and medical imaging. Additional interest. It was surprising that such a tiny particle has a fixed universal charge across all electrons. The oil drop experiment showed how simple apparatus, oil droplet electric fields microscope, could reveal fundamental truths about nature. Modern physics uses electron charge in semiconductors, superconductors, and quantum computing. If given more time, one could explore how electron charge relates to elementary particle physics and the search for possible substructures of electrons. Overall summary. The project was hard, but it was very interesting, and it kept me thinking about all the technology and science that goes on without majority of the world knowing. I think the most important thing that I learned is that electron charge is the foundation of electricity, chemistry, and atomic structure. The easiest part was understanding the definition and constant value of electron charge. For me, the hardest part was connecting historical experiments like oil drop and the cathode rays to modern nanotechnology. The most surprising thing for me was that Millikan's century-old experiment is still accurate today, verified by modern quantum standards, primarily because a lot of those have been disproven, or not a lot, but I mean a good portion have been disproven over the years. My takeaway is knowing a single constant underpins countless scientific fields and technologies. Physics, atomic models, quantum mechanics, chemistry, bonding, electrolysis, engineering, circuits, semiconductors, medicine, MRI, radiation therapy. It's a lot. And then there is all of, or that's my portion of the relevant sources, or at least majority of them. I'm pretty sure that's almost all of them, though. It was really interesting to learn about. Thank you.
Hi. Um, let's go ahead and start. My part E on my additional facts. Here's the picture and here's my source. Okay. Electrons can tunnel and appear on the opposite side of a barrier. It's a phenomenon called quantum tunneling, and it's possible because electrons are both particles and waves. And part of a wave can be on the other side of a barrier. This phenomenon is used in electron microscopes and modern integrated circuits. Another fact is that atoms lose electrons because of how they interact with forces beyond atomic nuclei. When an electron gains extra energy, it can become excited. This can happen when an electron absorbs a photon or a pocket of light or collides with a nearby atom or particle. Electrons can gain enough energy to leave atomic nuclei behind. These free electrons mix with ions to form a plasma. The third one is the negative sign associated with electron charge indicates its nature as an attractive force towards positively charged particles. Additional interests. Mnemonic 6.2, Part E, picture, source. Okay. My additional interests are that one thing that stood out to me while working on this project was how incredibly tiny the electron charge is and how important it is. Also noted something about the Millikan oil drop experiment, how fascinating it is because of how careful and precise the measurements had to be, especially like since it's still accurate 100 years later. Um, Another thing I wasn't expecting was how the electron charge connects to modern technology. Everything from microchips to phones to computers relies on electrons moving because of this exact charge value. I feel like if I had more time, I would probably go into depth on the modern equipment. So yeah. My overall summary. Overall, this project has helped me understand electron charge on a deeper level. I originally thought this topic was just a number we had to memorize, but it actually connects to a lot of different areas of science and layers. Like it's so like precise. Like the easiest part of the project was finding basic definitions and diagrams about the electrons. The hardest part was understanding the original experience, especially how scientists were able to measure such a tiny charge. What surprised me most was how consistent the electron charge is everywhere. It never changes, and the consistency is what makes electricity and chemistry possible. And slide 4. And here's my sources, and here's my screenshot of where it is in the book. And yeah, that's my part E.